This question is taken from the 2018 paper, so make sure you've got that in front of you. And like I said, this is just to give you an idea of what the questions look like, so that they're not completely new to you when you sit the test. So I'd like you to work your way through this question, maybe spend about an hour, watch the video, and as I go through each question, you can pause it, have a go at that question, and check your answer. Okay. Right. So obviously you can read this bit yourself. One of the main silicate minerals on the moon is calcium-based anorthosite, with the formula with calcium, aluminium, silicon, and oxygen. By treating the mineral as if it were made up of simple oxides, calculate the percentage by mass of SiO2 and Al2O3. And that's a fairly straightforward question. I think we can all have a good go at that. It's just working out the mass of this, and then the mass of this is the percentage of that, and the mass of this is the percentage of that. The only thing you need to be careful about is you need to think, well, how many SiO2s are there in here, and how many aluminium oxides are there in here? And it's quite a straightforward question to get you warmed up. All right, and moving on. So we're now going to talk about getting oxygen from this ilmenite, which is this iron titanium oxygen compound. Okay, they're classified as high Ti, high titanium, if they contain more than 2.5% of mass of titanium, and then we have this suggested method. Okay, so by considering its position in the periodic table, what is the maximum oxidation state of titanium? So you should be thinking about oxidation in terms of loss of electrons, and here's titanium, so you should be able to have a good go thinking about, well, how many electrons is that like? What's the maximum number of electrons that's likely to be able to lose? Okay. Give the formulae of the two oxides that may be thought of as making up the mineral ilmenite. So it's obviously one of them is going to be an iron oxide, and one of them is going to be a titanium oxide. All right, and you know that oxygen's got an oxidation state of 2 minus. All right, and you see here it says during the reaction the titanium remains in its maximum oxidation state throughout. So you've worked out what the maximum oxidation state is here, so you should then be able to tell, well, what are going to be the two, is it going to be FeO and TiO2, or is it going to be TiO and FeO2? And then once you've done that, we can see number 3, give the equation for the reaction between ilmenite and hydrogen. All right, so to extract oxygen from the ilmenite, one suggested method is to reduce the ore with hydrogen to produce iron, titanium oxide, and water. All right, so when you write the equation out here, you need to just be using this this line here. So you're going to react it with hydrogen to produce iron, titanium oxide, and water. All right, and make sure it's balanced. Assuming the average titanium content of the rock used in the process is 2.5% by mass, how many tons of moon rock would be needed to produce a ton of oxygen gas using this process? Okay, so you need to think about this. It's a two-step process, so I'm going to get a ton of oxygen gas. Where does the oxygen gas come from? It comes from the electrolysis of water. All right, so that's going to be H2O goes to H2 plus O2. So that needs to be balanced. Okay, now you're getting a ton of this. So that's 1 ton of that. All right, so you can think, well, if I have 1 ton of this, you work out the number of moles, that would give you the moles of water, and then from the moles of water in question 3, you can go back because one of the products in question 3 was water, so you can work out the moles of ilmenite, and then you can work out how much, if it's 2.5% is titanium, then you can use that to work out how many tons of moon rock there would have been. Okay, so you just need to work through those 2 steps. There'll be 2 equations. There'll be the equation from question number 3 and the equation from question from this electrolysis here. All right. So I think those are all fairly straightforward. So that's probably a good place to stop now and have a go at those, and then check the answers, and make sure you're on track there. Okay. Another variation is a multi-step process which starts with the reduction of the iron species present in ilmenite using methane. In the first step, 1 mole of methane reacts with 1 mole of ilmenite to form 5 moles of products, 3 moles of which are gaseous under normal conditions, suggesting an equation for this step. All right, so obviously it's going to be our FeTiO3 plus methane. Okay, and then we're going to get, I know that's 1 mole, all right, and that's 1 mole. I'm going to get 5 moles of products, okay, 3 which are gas under normal conditions. Okay, so some hints here would be that we're doing reduction of the iron species. Okay, so if I'm going to reduce the iron species, okay, remember it's not iron, is it? This is going to be an iron ion. If I reduce that, what am I likely to form? All right. And the second hint would be if this is being reduced, all right, then this is a reducing agent, which means that this is going to be oxidized. Okay, so you're going to be adding oxygen somehow to this. So possible products that you could have would be things like, so in CH4, the oxidation state of carbon is going to be, well, hydrogen's +1. So this is going to be -4. All right. And the only thing here that we've got that it can react with is oxygen. So a possible product would be carbon dioxide. Another possible product would be carbon monoxide. All right, and hopefully you've worked out that if the iron species is being reduced, then you're going to get iron. Okay, and you're probably going to get something else as well. Okay, and what you need to do now is you need to have a think about, well, if I'm going to get 5 moles of products and 3 of those are gases. Okay, now what that means is, so you could have, it doesn't mean 3 of the products are gases, it just means that 3 moles of the products are gases. So you just need to have a little bit of a play, think about, what else you could get. You could probably get some H2, or you could probably get some H2O, that kind of thing, and, try and work out what combination. You also remember you need to have the titanium, which hasn't been reduced, so it's going to be a titanium oxygen compound as well in here, and try and work out what that equation could be. And for this kind of question, once you've got something that balances, you probably just stick with that, as long as it matches all of these requirements here. Okay. All right. Probably a good idea to have a go at that and then pause it and check your answer. Okay, because that's quite a nice question. Right. D. Okay, so here we're given some thermodynamic data. All right. And this equation. All right. On heating the gaseous products of this reaction, these two, although not necessarily in the ratio as formed, so not necessarily in a 2:4 ratio, with a nickel catalyst, the methane is regenerated and water is also formed. Give the equation for this reaction. All right, that's a really easy question. Okay, because it's this plus this gives you methane and water. All right, so just write the equation out for that. The standard entropy change gives a measure of the change in the amount of disorder that takes place during the reaction. Amount of disorder in the products minus the amount of disorder in the reactants. Now, you see, this is new material, so you don't know this. Okay, now if you want to read about entropy, we'll do entropy next year. You can read about it in chapter 22. Okay, it is on page 362. There it is, entropy. Okay, but what they'll do is whenever they, and this is what will happen, they'll introduce a topic that you don't know about. Okay, and they'll give you a tiny bit of information about it. All right, so it's good now to go back and read about entropy, but here, look, it gives a measure of the change in the amount of disorder that takes place during the reaction. All right, so that's one really important piece of information. A measure of the change in the amount of disorder. And it says here, look, the amount of disorder in the product minus the amount of disorder in the reactant. Okay, so you can say that delta RS is S products minus S reactants. Okay. Now, would you expect delta RS for the reaction D to be positive or negative? Okay, so you've done, hopefully this question D was, what was it? It was CO plus H2 gives CH4 plus H2O. And if you balance that, you're going to need to have a 3 there. Okay? All right, so let's look more closely at this equation. Okay? Whenever we talk about entropy, state symbols are essential. So we have a gas, 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 and liquid. All right. Now, the change in entropy is a measure of the change in the amount of disorder. So, what's more disordered, a gas or a liquid? All right. What's more disordered, a gas or a liquid? Now, hopefully, you can have a good guess at that, and you can see that a gas would be more disordered. All right, so if you start with a solid, and you go to a liquid, and then you go to a gas, all right, solids are highly ordered systems. Okay, all right, and gases are highly disordered systems. All right, and so if we want to see this equation here, am I increasing the amount of order or increasing the amount of disorder? Well, over here I've got 4 moles of gas molecules. And over here I've got 1 mole of gas molecule and 1 mole of liquid molecule. So the amount of disorder over here is going to be very, very high, and the amount of disorder over here is going to be much lower. Okay, because here I've got only gas, here I've got liquid, and here I've got more moles of gas, and here I've got fewer moles of gas. Okay, and those are just some general rules. Okay, so it depends on the state change, and it depends on the amount of things that there are. All right, so for this one, you should be able to have a good go now at what you think that would be. Question number 3, calculate standard enthalpy change at 298 for the reaction between magnesium silicate and methane. So that's just working out the enthalpy change for this reaction, which you can do. That's a question that you know how to answer. All right. Question 4, calculate the standard entropy change. So the standard entropy change is this equation here that we were told about. All right. So even though we don't know anything about this, we're told how to do it. All right. Just you'll remember from the organic, it's the same thing. It tells you something new, and then you have to use it. Okay, so you should be able to do that as well using that equation. All right. So probably have a go at those, and then just check your answers. Make sure you've got the maths right for those. A further thermodynamic quantity is the standard Gibbs energy of the reaction. We'll do this as well next year. Okay, you're given the equation, and you're told, look, if delta G is positive, the reactants are favoured in equilibrium. If delta G is negative, the products are favoured in equilibrium. Okay, so calculate delta G at 298 Kelvin for the reaction between magnesium silicate and methane. All right, so you've worked out up here enthalpy and entropy, right? And all you're going to do is you're going to take your enthalpy answer, put it in here, take your entropy answer, put it in here, and 298 is the temperature. Okay, so it's just this number minus these two numbers multiplied together. Very, very simple. The only thing that you need to be very, very careful about is units. You need to make sure the units all match up for this. All right. Now, if we go and look up here you can see that your delta H is given in kilojoules per mole, your entropy is given in joules per Kelvin per mole. So if you wanted to have these two in the same equation, you're going to have to multiply all these by 1,000. All right, that's going to happen. And then you can see that you should be able to then work out what the units for delta G are. Okay. And then, assuming that the values for delta H and delta S do not vary with temperature, calculate the minimum temperature at which the products will be favoured. All right, so this is a very common question that we'll come across next year, but essentially what it's saying is, at which point does it change from being reactants favoured to products favoured? Okay, and that's when the delta G goes from positive to negative. And delta G goes from positive to negative when delta G equals 0. So essentially you just need to solve this equation. 0 equals delta H minus T delta S. You just need to solve that equation for T. All right, and that's good. So check your answers for that, and then we can have a look at section 3. So ion plasma separation, nice bit of interesting chemistry to read about here. And then suppose a rock is composed, it's important that you do read this, okay? I'm not reading it just to save time on the video, but it's important that you read it so you have an idea of what's going on. Suppose a rock is composed of the elements O, Na, Mg, Al, Si. Arrange the elements in order of the first ionization energies. Brilliant. Okay, so you can do that, no problem. All right. Be very, very careful. Remember all the rules for ionization energies and changes in energy. Okay, so shells and subshells. Do that, check it. All right, hopefully you get it right. Here, given an equation, all right, looks disgusting, but most of these are constants. Deduce what units the constant C must have. All right, now alpha is a fraction. This is a fraction. All right, which means it has no units. Yeah, 0.2. All right, is let's say when we're doing if we had, when we did the Arrhenius equation, the prefactor is the proportion, so it's just like it's a percentage, isn't it? All right, there's no units. Okay, and the exponential factors, they also have no units. So this here, E to the minus EI over RT, that has no units, and you can know that because you can do this is the first ionization energy, so that's an energy that's going to be joules per mole. R is joules Kelvin to the minus 1, moles to the minus 1, and this is Kelvin. And if you multiply all those together like it is here, you get no units. All right. So this has no units, this has no units, so this has units, and C has units, and this has no units. So you should be able to work out, essentially what it needs to be in order for it to cancel with this temperature. Okay, so have a go at that. And then the last question. A given sample of rock contains these elements at the temperature of 10,000 Kelvin. This are all more than 50% ionized. Okay, which perhaps now gives you a clue. If you weren't able to do this one, you might be able to guess which has the highest first ionization energy. Given the first ionization energy of oxygen is that, use the equation given to calculate the percentage of oxygen atoms that would be ionized at this temperature. All right, so look, you know what C is because it's this constant here. You know what EI is because it is the ionization energy. You know what R is because it's given here. You know what the temperature is because it's given here. So you know what all these. So this question, this is easy. Okay, how many marks do you get? You get 4 marks for doing this. 4. That's loads of marks in this kind of paper. And all you're doing is putting the numbers in the equation. Okay. Only thing you need to be careful of is the units. All right, because your gas constant is in joules, and your energy ionization energy is in kilojoules. So make sure that you've got those right. And then that's it. Have a go. And you know, because it's percentage. If it's not between 0 and 100, it's probably not going to be right. All right, and it's probably going to be less than 50%. So that's a good one. All right. Good luck.